Hi, and welcome to Concept Base. I'm John Hepworth. And this is a Year 11 extension topic that we are in here, further work with functions. We're in the parametric forms section, and we're looking at, well, I'm going to give away the answer. We're looking at circles. The reason why I want to look at this circle question today is because students get rote taught a very specific way to do parametrics with circles. And I just want to demonstrate to you what could happen if you go down the dark path of not doing it exactly the way that you've been taught and maybe trying to do it the way that you thought you had to, which is the same way you did the linear functions and the quadratic functions. So like you forget the trick. Forgetting the trick's okay because hey, mathematics is mathematics and things work out in the end anyway. As long as you don't make any algebraic mistakes, then you should always get the same answer. So I'm going to do this question today in a pretty non-standard way. I'm going to do it in the way that you would do for substituting in linear and quadratics, and let's see if it works. Then I will do the quick way and show you that that's definitely something you should be looking for. But I do want to give you the confidence that exploration is okay. And if you understand the concept of substitution solving these parametric equations, then go with the concept. You don't have to remember the rule that gives you a specific way to do it. Okay, so the question is, given the parametric equations x equals 3 cos t and y equals 3 sin t, describe the features of the resultant function. So let's say we wanted to do this as a substitution method. All right, so we've got x equals 3 cos t, and we need to make t the subject. So to do that, we're going to get x on 3 equals cos t, and then we're going to do the inverse cos function, and we're going to get t equals the inverse cos of x on 3. We are then going to go and take that and substitute it into our y equals 3 sine t equation. Right, so y equals 3 sine t is the other equation, the other parametric equation, using t as the parameter, which I discussed in the previous video. If you're not sure what's going on with these parametrics, watch the previous video. Okay, so now we're going to substitute t in, and we're going to get y equals 3 sine inverse cos x on 3 like this. Now, the reason why I want to go this way is because I want to also make sure that you're feeling comfortable when you see these trig functions of inverse trig functions, or inverse trig functions of trig functions, or trig functions of trig functions. Sometimes they pop up in extension, and we want to know what it is that we're dealing with. Now, we are at the crucial point in this question right here where I want you to do what John Hepworth always says to do to his students, and they don't always do, and that is, are you a fan? Draw a picture. Draw a picture. It's going to help you go through this part of the step in this question. Because what are we looking at here? Well, we're looking at an inverse trig function. So we're finding an angle. And the inverse trig function is cos. So that's adjacent over hypotenuse. And we've got x over 3. So we can actually just make a triangle. Make a right angle triangle. That's the only way trig works. Make a right angle triangle. Okay, so now once we've got the triangle and we know what the answer to this part here is, which is theta, we're now doing sine of theta. Now, sine of theta is opposite over hypotenuse, but we don't have an opposite side. But thankfully, Pythagoras theorem will get us through that, and this will be 9 minus x squared square root. Square the long side, subtract the square of the short side, take the square of the answer. And now we can do sine theta. So we can say y equals 3 lot solve, and sine theta is opposite root 9 minus x squared over hypotenuse, 3. Okay, so we managed to get through the trigonometry, and we got into the substitution, and we got through it, and we're now at the point where we have a resultant function, or relationship in this case. So now we just go ahead and further solve. This 3 is cancelling. And we have y equals root 9 minus x squared. Now let's get rid of the squared, and we're going to get y squared equals 9 minus x squared. Let's add the x squared on the other side, and we get x squared plus y squared equals, I'm going to write 9 as 3 squared. And hopefully you're recognizing that this is a circle with radius 3. So we made it through using the substitution method and not some sort of trick that we've been taught. by just using the same concepts that we've always used, where we're trying to make the parameter the subject in one equation, substitute it into the other equation, and then solve that equation. Well, not solve, but get it into a function form. So the question does say to describe the resultant function. So I would say, therefore, say that we have a circle. And the thing we care about with circles is where its center is. A circle center at 0, 0 with radius equals 3. That would be the features that they'd be looking for. They might be looking for a domain and range. If they are, we are doing a domain of inclusion of -3 to 3. And we're doing the same for a range because this circle is centered at the center. Okay, so that's the concept way and algebraic understanding and trigonometric understanding of how to get through a trig function of an inverse trig function. Now let's look at another way of doing it, which is the way we get taught. And that is if x equals 3, I think it was cos t, and y equals 3 sine t, we can get a shortcut of putting these two parametric equations together by looking at our trig identities. And the way that you can put cos and sine together, well, now, you were going to learn how to put it together without it being squared in the future. But looking to put them together at the moment, we need to square them. So we would say x squared equals 9 cos squared t, and y squared equals 9 sine squared t. Then we just add the two together. So we get x squared plus y squared, adding the left-hand side of the equations, equals 9 cos squared t plus 9 sine squared t. And then we can factorize that 9 out. And we're going to be left with cos squared plus sine squared, which is sine squared plus cos squared, which is 1 based on our identity. And here we have arrived once again at the circle that we arrived at via algebra. Certainly quicker, okay? So this is one of those ones where you remember a rule, you substitute it in, you get an answer out, and you get there quickly. So the reason for me showing that previous method that's a little bit more work is just that if you do find yourself going down a dark path of into the wilderness of algebra, it's okay. As long as your algebra you don't make mistakes in the algebra, you should come out and see the light at the end of that dark tunnel.